Okay, it's on. So this is assembly level programming, and I just want to brush up a bit because tomorrow is going to be a paper, right? So an examination. So let's start the intro. So you have these flags in the 8085 processor: sign flag, zero flag, auxiliary carry, the parity flag I think, yeah, and the carry flag. Sign flag is turned on, which means it is equal to 1 after an arithmetic operation. It will be equal to 1 if the result, that is the thing in the accumulator that has D7, so this thing as 1, or else S is equal to 0. So this S7 is actually used, the D7 thing, the 7th bit of the thing in the accumulator, that's actually used for sign. So for a signed integer, that gives you, I mean, if it's 1, it will give you a negative integer. It will represent a negative integer, and if it's 0, it's a positive integer. For unsigned integers, that's different. Then it is also uh, just a unit in that thing, right? So yeah, right. That will be the 2 power 7 thing. So if it's 1, it is 1 into 2 power 7. If it's 0, it's not there. You get it. And then you have the 0 flag. So if the result is 0, then this turns on, otherwise it doesn't. Auxiliary carry, so this is not important because it's not programmable. Parity flag, result has even number of ones, then parity is equal to 1. If odd, then 0. So it's kind of weird actually. I'm not used this flag. I mean, I've not seen this flag in any of the examples in the textbook from where I'm reading all of this. And yeah, so the thing is, if result has even number of ones, then parity flag will be 1. If not, then 0. Carry flag. When result can't be expressed as 8 bits, it needs 9 bits. 1 for sign, 8 for magnitude. That's for signed integers. For unsigned, you don't need that extra bit for the sign. You get it, right? And you said carry equal to 1. So whenever you can't express it in 8 bits, you need 9 bits. So what do? We don't have 9-bit, I don't know, 9-bit registers or memory locations that can store 9 bits. So what we do is we put that extra bit into a flag, so later on we can use whatever that value was. So if it was 1, we will add it to that, and yeah, understandable. OP code, so operation code, like it's just 8-bit numbers that represent machine cycle, so that represent the instruction that we want to give. And then what you have is like a compiler takes the mnemonics that we will give it, that's the code basically, and it will convert it to operation codes, and then it will feed those operation codes into we will feed those operation codes into the actual hardware, or it will do it directly if it can. Yeah, and that will run the machine cycles. So the whole thing about this microprocessor is that it runs on timing basically. So first you want to do a bunch of instructions, then you want to do a bunch of, so like it has some importance of time over here, right? So that's why we need these machine cycles, because they tell each component of the microprocessor at what time should they do whatever they want to do, so that everything actually works together to give us something constructive, and not just like random random voltages that would be bad, right? That's how a microprocessor works, at least. Yeah. uh Okay, so that's just the intro. Let's go to data transfer. Okay, let's maximize this thing. So first we will have all the load instructions. So LXI, this is load immediate, and it's like load immediate into a register pair and address. So register pair is just uh, two registers that are side to side. So it could be the H register pair, which is the H and L registers, or it could be the D register pair or the B register pair, right? So when we say uh, LXI RP address, what it does is that whatever address we have put in this instruction, it will put that address into the register pair. Okay, so how does it do that? It puts the lower bit of the address into the L register pair and then H register pair if your register pair was H, right? So H represents both HL, right? Use H, not HL for register pair. Okay, LDA address, so it's load accumulator. Accumulator is just the A register that like is the most important thing in this, right? It's a part uh of the ALU, or you can say it's kind of like the part of the ALU, and yeah, it's like really important because that's where all of the results are stored and all of the operations take place and stuff. So LDA, that just means load accumulator with address. So whatever is inside that address location, you will load that content of the memory address into the register. Then LHLD, it says load HL register pair with this address. Okay. Oh no, it's different. Okay. Not with this address, instead with the accumulator. Sorry, instead with the contents of the address. Okay. So LXI, right? LXI was for loading addresses. LHLD, that's for loading actual content. So it loads the content of address into L and contents of address plus 1 into H. Right. Okay. Yeah, this is fine. This is fine. Then wait, I think it was that in this LXIH 4000, what you had to do was you first would put the OP code for LXIH, and then for this address you would first put the lower byte, the lower byte, and then the upper byte, the higher byte. I think that is how you had to do it. Anyway, I just spaced out for that a bit. And what were we doing? Okay, LHLD address, it loads the content of the address into our HL pair. So content of the actual address that we gave into L, and then the content of address plus 1 into H, right? Cool. And then move RM, this is like an important thing, so we were using this a lot. So it moves the thing into like move the content of the address on the HL pair into the given register R, right? So yeah, it's just like a 1-bit instruction, I think. Sorry, 1 byte yeah, because it just needs one OP code, it doesn't need anything else, right? So move, for example, AM and move BM, both of these will have different OP codes. Okay, then you have LDAX register pair, so it's load immediate but accumulator, so you can load the accumulator immediately as well, right? So just to review, you have load immediate any register pair with an address, So for example, you can have LXIHL, sorry, LXIH, because yeah, not HL, just use H, with some address. Then you have load accumulator with an address, right? So the content of the address, that's what I mean. Then you have LHLD address, so it's load HL pair with the contents of the address, right? Okay, and then you have move from memory. So HL is basically the memory. HL pair is the memory into the register pair R. Right. Then you also have move R1, R2. That is also a thing. So it moves the content of register R2 into R1. So the first thing is always where you are moving, and the second from where you are moving. So here too, you are moving into the memory, right? The actual address, like you're putting the contents of the address on the memory as the contents of this register, right? So both of these will become equal after this operation. But where we move RM, okay, and then you have LDXRP, so it loads the accumulator directly with the contents of a register pair, right? Yes. So it you have like multiple ways to load the accumulator. You can load it with an address directly. You can load it with a register pair. You can load using this thing. So you can have move a comma m, and that will load the accumulator with this memory. So there's actually two ways to like load a using the memory. You can either do this thing that you can load accumulator directly using the register pair a using the register pair h, right? Or you can do this thing, move a comma m. That would work as well. Okay, next you have input instructions. So now we know how to actually get uh, how to get stuff from the stored data, and now we want to put in data. So you can move immediate into register data, or you can move immediate into the memory data, right? So this is kind of nice, right? Yeah, so you just need to put an address into the memory. So load immediate h comma address, that's what we do, right? Yeah, and then use this command to put whatever data you want into that memory location. So this is like nice. And similarly, you can use a register for instant reference of that data. Okay, then you have a store instruction. So like store instructions have storing from accumulator to some address, storing from HL pair to some address. So you had load into HL pair from some address. Now you also have store from HL pair to some address, right? Yeah. And what STAX register pair? Okay, so the contents of a accumulator just go into the address written on this. Okay, and this is like an important thing. So you can move into memory from register pairs. So like this is the one that we use a lot, I think. Okay, data transfer instructions. This is important, but I already discussed this. And then exchange, this exchanges H with D and L with E, kind of. I don't know, why would you want to do this? I think it's just a shortcut, so like you can do it easily, kind of thing. But yeah, if you did not want to put some kind of address into HL first, and like why would you want to exchange? Like there isn't, okay, whatever. Maybe we'll see a condition that we have to do it some day. Okay, then set carry, it just sets carry equal to 1. Oh, so this is kind of nice. So yeah, this is nice. It just sets carry equal to 1. So how would you make carry equal to 0 though? Oh yeah, that's kind of, how would you do that? I have no idea. Anyway, so that's data instructions and stuff. Okay, cool. And then you have arithmetic and logic operations. So let's go. So you already know all of this. No big deal, right? Arithmetic instructions. So add R, add M. Anything that starts with AD, you just know that it's involving this accumulator thing. Why is this? It shouldn't be like that, right? Now it looks good. Control S. Oh, this is done here as well. Okay, anyway, where was I? So add R, it just adds the content of the register into the accumulator, right? Add M, just the contents of the memory into the letter, right? So it does A plus equal to and pi plus equal to M, just A equal to A plus content of M. So why content? Why did I write it like this? Because M has an address, so the address, the content of that address, you get it, right? Then ADI data. So you can, I mean, yeah, like you used to have that input instruction load immediate, no, sorry, move immediate, right? MVI data, that was one thing, and you also have ADI data, which adds data directly. So that used to move. This is going to add. Okay, and it's only for the accumulator, of course. Then you have add C, so it adds with carry, and this adds with, I really like these three, but then these are simpler to actually use, right? So if carry is 1, then add it like that stuff, right? Yeah, this is nice, I think. Okay, cool. And carry, this only changes when we do some kind of arithmetic operations, so you don't have to worry about the changing when you like what should I say, when you do jumps to other. Okay, we will talk about jumps later. So what is ACI? It's add with carry immediately. So wherever you have C, you have carry involved in it. And it's the same thing, ADC, AD. So what does D mean over here? A double, okay, that's just for add. Yes, sorry. And this C, because you couldn't put A double D C, then that's why you had to put ADC for short. Nice. So ACI, that doesn't look like it's adding, but it is adding, right? Everything that starts with A, that is probably adding. Yeah, and everything that starts with S is subtracting, whatever. So same thing as addition, is the same thing, right? Any extra thing over there? No, it's not. Oh, and by the way, instead of having carry, now this thing has B over here, which actually means borrow. Hope that makes sense, right? Yeah, borrow. Because okay, so this is like important when we will use binary coded decimals. I think, yeah, that's what we do. But also for like normal hexadecimal numbers, you can use this, right? You can use this. So if you have an already pending carry, you need to get it away from some other number, and you will use this thing. So this is nice. This is very nice. And then what? And it's kind of a weird thing, but like a byte, it uh it has like 8 bits, and that means it's, yeah, it's, how would I say this? It's like 2 power 8, but then 16 is just 2 power 4, so it's actually like two hexadecimal numbers. So we should probably say uh like 2 power 8, that's just 256, whatever that is, like that as a base, whatever that's called, right? You carry with that something like this. Okay, no, let's move on. Yeah, you understand what I'm saying. Like for carrying, you use bytes as parts of the number with base 256, if that makes sense. Okay, right. And then what you have, increment. Uh, so you can increment register pair directly. So it's a bit, it's address, it's not the content anymore. So when you say increment h, what that does, I mean inx h, what that does is it increments the actual value in that h, the actual address, not the content. And when you say inrm, that actually increments the content. And similarly, why is this having this, oh, oops, tab. Okay, it's not supposed to be there, but it is. Why is this so irregular? Okay, now it looks better. Right. So increment register pair, and you'll have INR, that is increment register. And I mean M is not a register, but you get it, right? It increments. And then decrement. So for decrement, once again the same thing, and then you have DAD. I don't know why it's called DAD. So it does M equal to M plus register pair. Huh. Weird. Very weird. What is this supposed to mean? Why would somebody use this? Okay, comparison. Important. These two are important. So when you compare with anything, so register pair or memory, what you're doing is you are actually subtracting the contents of that thing with accumulator, and actually not showing that in the accumulator. So accumulator is still what it was before, but you did the subtraction, and the actual process of that subtraction that changed your z and carry. So your 0 and carry flags, they were changed. So if your comparison is that both of these are equal, then your 0 flag will be set to 1. And if your comparison is uh, that the given number was bigger than what's in the accumulator, so the accumulator was falling short, then you can do, like, then you will have carry equal to 1. So you compare this number r with uh yeah, you compared the number in r with the accumulator, and it was bigger, and that's why carry equal to 1. If it was smaller, it would have carry equal to 0. Hope you understand that. Right. And z would still be 0 if it was smaller or bigger, because it's not equal. Okay, then you have this Boolean logic thing. So you have two things, one's complement and two's complement. And one's complement is the actual complement that we will refer to over here. So this is the complement. Or it's the complement of the carry. Sorry, this is the thing. So a equal to complement of a, CMA. And it's the same thing as saying not a. If you are from a math background, you would know what this thing is. Actually, everyone knows what this is. So not a, if what it does is like it takes all the bits of a and does the not operation on those bits. So if your 0th bit in accumulator was 0, then it would turn to be 1 after this operation, and so on for every bit. And then you have other operations, and operation, SOR operation. So SOR operation is like OR, but a little different. Okay, so what does this SOR operation do? When both of them are zero in OR as well, just get a false, right? In you get a zero basically. But in XOR you also get a zero when both of them are one. So that's why it's called XOR. So it's either that or this, not both at the same time, and not none of them at the same time. Right. And then you have and OR, of course. So what's like these other things? So XR, OR, AN, these represent the AND, XOR, or OR things. But these three things, these two things, A and I, these are, so all of these are just on the calculator, of course. Why is this so irregular? I didn't have it so irregular the time I saved this. Okay. Right. So you can do it immediately. So it will just set your accumulator to be the previous accumulator and data, the operation of those two. Yes. Okay. And what's all of this? Okay, these three things, these are not for these three lines. These are for the whole AND operation. So whenever you do an AND operation, you have that carry is cleared. So it's zero now, and AC is set. We don't care about AC anyway, so yeah, whatever. But carry is cleared whenever you do this operation. And then, yeah, cool. Right, so it's nice, I think. And what's the twos complement? It's just the ones complement plus one, right? Or I should say 0 1 hexadecimal. That would be a twos complement. So this is arithmetic and logic operations. I don't think I can memorize all of this in one day, because like I have to memorize how it works and like all these tiny details, what things it can take, what it cannot take. It's gonna take a lot of time, but I will hopefully do that. Anyways, so whatever programs I will write for this video, I'll be using all of this stuff that I've written down. But yeah, I should technically first memorize it and then do it. But I think while writing programs, I will memorize it, because I will use it so much that I will just have to know how it goes after writing it so many times. Okay, so that's data transfer and arithmetic and logic. And you also have all of this stuff. So how stack enables regards, it's like something what stack pointers, if and while. That's okay, that's not actually an introductory process, but yeah. Jump, this is important. Ports and interrupts, not so important. Rotation, kind of important. Stack is not that important because they don't use it that much. It's only behind the scenes, it's working behind the scenes, but they don't actually use it. But still, like in this jump thing, you can get all of this stuff. So yeah, I should probably explain what a program counter is. Actually, I didn't explain, so it's over here. So I didn't explain what stack is, and that I will after we are done with writing programs, because that's not involved in writing programs actually. So a program counter, it stores the address of the next instruction to be executed. What is next one? Okay, program counter stores the address of the next instruction to be executed. The address with that is which the OP codes are put in tells about the sequence in which instructions are executed. So you just imagine like a bunch of OP codes we enter, but where do they go, and how does the computer know when to execute which OP code? Does it run in some kind of sequence? Yes, it does. So it's all stored in stack, and then the yeah like and then the program counter it okay, how do I tell? Sorry, it's not stored in the stack. It's just stored in a list. Remember that it's just stored in a list. I don't know how to explain this clearly. Yeah, and then the program counter it just points. It's like a point. It just points to the location where the OP code is stored. And sorry, I think I'm describing stack pointer for some reason. Sorry, this is completely different. Okay, calm down. What was I saying? Program counter. So it stores the address of the next instruction to be executed, right? What I was describing was something like stack, which I shouldn't have done, but yeah, program counter stores the address of the next instruction to be executed. The addresses which the OP, oh, actually no, it does store the address of the, so I was describing, okay, this is getting complicated. Just forget everything that I said of like related to program counter before this, and let's start from fresh. Read this. Program counter stores the address of the next instruction to be executed. The address of the next instruction. The address which the OP codes are put in tells about the sequence in which instructions are executed. So yeah, that's exactly how I described it the first time. Then I got confused whether it's the same thing as stack pointer or not, but it's different. So yes, it's a pointer. It will point to the OP code's address. So it has the address inside it, right? It's a 16-bit 16-bit thing. It's not a register. It's not like, I don't know what to call it. So it just has 16 bits in it, and those represent an address, and that address is having the OP code instruction inside it. So it's a byte, right? It has that inside it, and that OP code that represents a machine cycle. So yeah, like however the control thing works in the microprocessor, it just reads that OP code, and then the program counter increments or decrements depending on how this list is. Alright, and then branch instructions alter the sequence. So that's basically the jump instructions and some other instructions as well. Okay, so the simplest jump instructions just jump to some address, and I did write this address over here, but the way you will be writing this code actually is that you will have, how do I say this? I mean, it's okay on that thing directly physically. If you want to type in on the 8085 processor, you will have to put in the address in there. But what you can do on actual good software on a compiler is yeah, instead of doing this, you will put a label on one of the instructions, and that label you will put instead of its address. Okay, so that label represents an address, but it's not actually an address. It's just that we do this in the compiler so that it can run correctly, but on the actual hardware you can't do this. So you just have to put in the address and the OP code for jump, right? And that will be given by the compiler, so don't worry about that. And you have conditional jumps. These are the most important things, because it's like yeah, it can be used so many times. It can be used for building a while loop, for an if statement, right? So conditional jump, jump non-zero. So when the result of an operation, or Okay, I should not say the result because it's not related to a result. It's individual. It just checks the zero sign flag, sorry, the zero flag, and if the zero flag is zero, right, it's off, then it sets the program counter to whatever address we put in, and by address I mean the label, so it points to that step which we labeled, and that's why it's called jump on not zero. And then this is similarly jump on zero. So if your z is 1, so z being 1 means that yeah, like some operation gave 0 in the computer, and that's why z was 1. And then jump non, oh okay, jump on no carry. So when carry is 1, wait, what? uh Jump on no carry, right? So why is this if carry equal to 1? Okay, I think I just go back to that ALP intro thing. I think I misunderstood what carry was doing. So carry flag, when result can't be expressed, right, then carry is set as 1, right? So jump on non-carry, that should probably have carry equal to 0, I think. Where did it go? Where did it go? Jump statements. Yes. So this is not correct because clearly by the name it's just jump on not carry, and it should be carry equal to 0 probably, right? And then what's jump on carry? If parity equal to 0, oh, I think something got messed up over there, right? This should be carry equal to 1. So if carry equal to 1, then do this thing. If carry equal to 0, right, as the name suggests, it should be just like that. So if carry is 0, then jump, otherwise don't. This is what jump on not carry does, and then jump on carry does the opposite of that. And then jump on odd, jump on even, related to parity. So when in parity is 0 and jump on even is there, it just jumps and so on. Okay, and then what? Jump on plus and minus. Oh, okay, not that bad. I mean, you can use this while comparison, I think. Mhm. Yeah, I mean, I don't understand why don't they use sign flag while comparison? Why don't they set carry flag? Oh yeah, because for signed. No, wait. It They could have also used the carry flag. Oh, sorry, they could have also used the sign flag. Why did they use the carry flag? No idea. But they use carry flag, so just have to deal with it. I really do wish it was sign flag because it looks more intuitive, to be honest. That's the only reason. Okay, anyway, next. So that's jump statements, data transfer, yeah, all of that. Rotation. So as the name suggests, it just rotates the number. So it can rotate through a carry, or it can do this thing. So rotate left the number greater than through carry flag. Uh, yeah. Once again, why is this the way it is? Did this happen by itself? Okay, so rotate left the number in accumulator. That's what RLC does, and it sets the carry. That's this thing. Okay, and oh, so these work differently, but both do the same thing, except what they do, the carry flag. So when we say rotate left the number in the accumulator, uh, first it will do a new, so accumulator n plus 1 new of that, like that will be previous. Okay, I understand what's happening. Oh, so it's like the seventh guy, it will just go to the carry flag. So the previous seven, it goes to the carry flag, and then sixth goes to seven, then fifth goes to sixth, and so on. And then from that carry flag, you feed into the zeroth digit. Yes. Okay. And what does RAL does? Rotate left the number in the operator through the carry flag. Is this different for some reason? Oh, it is. So here carry was the previous seven thing, and now here it's the new A0. I mean, but wait, both are the same thing. Oh, so then okay, fine. Wait, something's different. Okay, and I understand it. So first carry is previous A7. Okay, then this thing. Yeah, I mean it's the same thing as that. What's the big deal? Huh? How are these two different? Rotate left, rotate right, and this thing is still so like rotate left through carry and rotate. Oh, it should be opposite of each other. And okay, something I didn't understand well while writing this, I think. But yeah, I think these two actually do work because it seems intuitive. Okay, that's nice. And that's rotation. Then you have stack and if and while. So what do we have in if and while? Right, this thing. So it's an actual program. So this is a loop, right? This thing is a loop. This thing is a comment. So whenever you have the semicolon, the next thing to it is just a comment. So it moves immediately into C 08H. It checks if, oh, so this check is a label. Then decrement C. Okay, cool. And jump on non-zero, check. Huh. Right, and inside of all of this, right, so inside of all of this, you can put whatever you want. So all these stuff that you want. And this is how a while loop works. So while C is not zero, just keep on decrementing it. It's more like a for loop really. But yeah, that's how a loop works in here. And then you have an if and if else statement. So jump do condition, okay, fine. Then jump end. Oh, I understand what's happening. So it's more like a function call, but instead of going back to the definition, it's going on the front of the definition. So yeah, it doesn't return to the actual statement where we call the function. Instead, it goes to this this statement where we like terminate everything and we move on. Okay, that's how it is. So you have these conditions if, elif, and all of these are just jump conditions, right? And So condition get put as per need, right? And where do they jump? They jump to whatever you want to do when these conditions are satisfied, right? And like when you have the if this label's condition is satisfied, it jumps to this do label, and then once it does whatever it has to do, in this case it's just NOP because I don't want it to do anything. So NOP is like do nothing. That's what NOP means. And then it jumps to this end label, which is also having NOP, but yeah, you get what I'm saying. It just checks for a condition, it jumps to something that it can do, and then once it's done with that, it jumps to a final label that everything jumps back to, and we move on, right? Okay, so I think that's enough. We will be starting actual coding now, right? Jump, if, while, rotation. What else could you possibly need? Stack connection and how stack enables recursive functions. We will do that, but after the coding. Okay, so I'll just minimize this and we will open this guy. Okay, so yeah, this thing is Sim8085. It's a website, and it's basically simulating 8085 because instead of buying 8085, why not just simulate it, right? It's just an outdated microprocessor, so I don't think they even like sell it like they sell microprocessors generally. So yeah, we just need to use this thing, and yeah, this is a nice piece of thing. We'll be using this. So as you can see, they have put these comments and all of this, and we'll just delete all of that. I will just delete all of this. So the halt comment or halt comment or whatever you call it, it halts the program. Right. So let's see what programs we could be doing. Let's start with something basic. Okay, so you have. So I just have a textbook which has a lot of questions in there and stuff. So we'll start doing questions from them. A block of data is stored from location 2001 and onwards. So we'll go to address 2001. 2001. Right? Go, enter. Where is 2001? I cannot see anything. This thing is 200, but where is 1? Why is this 2? Wait. Start address at. Huh. What's with this thing? Oh, okay. No, I just want to go to this address. What's the big deal about it, man? Okay, something's weird about this. It's not going the way it should be. So this thing is 110B and stuff. Oh, okay, I understand what's happening. So we'll just start again. 2001. Right, and this thing is the 2001 address. Right. So I just want to edit this. I'm gonna put something. What do they want to put? A block of data is stored from the location 2001. So something like 22 and 0C, huh? That's weird. Oh, that's weird. Should this actually be happening? Okay, whatever. BB. No, oh, it's 66. That's not B. Anyway, you get what I'm doing, right? Okay, fine. And so it's just a block of data from 2001 and onwards. The count is stored at 200. So I'm going to say it's three of these. So there's only three things, right? And then what? Write an assembly level, okay, assembly language program to find out the sum of the data items stored in this block. So you want the data items stored in 2001, 2002, 2003. You want to have the sum of those. Okay. Store the result in 2500. Okay, we will do that later. So 2500, that is, it's not here. We'll do that. And onward, starting with LSB. LSB, what does that mean? Oh, okay, lower bits, I think. That's what it means? Lower bits? Yeah? Maybe. Right, so first of all, you just need a program to actually add all of these. So it's 3 in 2000. We want that count somewhere, so we'll just say move, it should be move MOV, and it will be to register, say B, because you're already using A, so why not use B, comma. So move into B, what? Contents of this guy, right? Maybe I should just use move immediate. No, that would just have the, yeah, that's kind of problematic thing. I just want to move the stuff in whatever this address is into this register. So one way to do this, like it's like that, or I could load the register from the, not from the memory. I need to load it from an address. And was there a way to do this, to load it from the address? I don't think so. I think we should load it to the HL pair and then to the register. But can we do it directly? So data transfer. Okay, that's one thing. Load accumulator from address. No, that's not what I want to do. No, you can only load the accumulator directly from an address. You cannot load a register. That's bad, but that's how it is. Okay, so we will have to put this into the, or we could also just load the accumulator directly and then move this into some kind of thing. Yeah, but the best way is just to first of all do this. So load immediate the H pair, and we'll load the address 2000 H into it. Okay, so now our HL pair has 2000 address into it. Next, what we want to do is get whatever this count is into a register B, for example. So it will be MOV. Our register is B, and we are moving from the memory. Okay, then I want to increment our HL pair. Autocorrect, man, seriously. Okay, so we will incremented our H pair. I think this should work. If it compiles, so that will work. Okay, and we have also moved whatever is in our memory into B. Now we can start. So now we need some kind of loop that will decrement this b until it becomes 0, and when it becomes 0 we run out of the loop. And while the loop is running, we will we just want to add whatever this is into our accumulator. Now this can be complicated because like 2 plus 6 that is 8. But what if there were bigger numbers? So in that case it could go like to a much bigger thing, and that would be problematic thing, right? So yeah, it could be so many, it could be so big. How do we like have that work out if it can be that big? Oh, come on, think of it. There's also going to be carries and everything involved in it, but right now it's not all that bad. It's just 2 and 6, so it's going to be 8. But if it was bigger, you would have a carry and you would have to deal with it. But how would you deal with it? You can definitely store the 2 digits that you got somewhere in 2500, and then you would store the next digits that you want into the next thing. That's a bad idea. How I'm going to do that? Okay, but for this much it's not that complicated, so we'll just do that, right? And now what do? We set up a loop, but before that maybe we should take the whatever is in the accumulator, right? So we'll just move. Oh, we'll just load immediate. How do we load immediate? It's LA, I think. No, load accumulator, but immediately. No, that's not. Okay, whatever. MBI, that's gonna work anyway. So move immediate into a register pair, into a register A, data. And what is data over here? It's just 00, right? I will put 00. So this will be the starting value of A, and then we will just keep on incrementing A by whatever is in these values. That will add 22 to it, and then so on and stuff. Okay, cool. Right. Okay, and then we'll set up a loop. So we'll put loop right. What should be the first line for this loop? Come on, think of it. What's the first line for this? Just put all 3 lines to it. So you will increment your h. Maybe that's one thing that you can do, right? Maybe that's the first line that you should be doing. No, but you already have something in h over here, so okay, cool. Then we just integrate, just do this thing. So once you have incremented your HL pair, now it's going to 1. Then you need to add it to A. So you add, I think it's just ADD, and it's from the memory. Is this correct? I think it is. Right. You can add immediate by putting in data. You can add by the register or by memory. You can add using carry as well. So that's the carry. Okay. Okay, fine. And then what? And once you have added M, what do you want to do next? You got it in accumulator. Now what? Now we need to store. No, we cannot store yet. So now we just need to run out of the loop, I think. Or what if we store every time? No, that is probably not a good idea. So we just run out of the loop. And how do we do that? We can decrement b and check if it's non-zero. So jump on 0 to loop, right? So if b becomes 0, then we just, sorry, it should be jump non-zero on. Okay, so when b is not 0, we just jump back to the loop and keeps on going. So we start from b equal to 3, so it will take 3 such loops to get out of it. So it will run for 3 times, because 3 to 2, then 2 to 1, and then 1 to 0. And then once we are out, we just need to report back this value that we now have in the accumulator into some memory location. So it's just store sta, I think. Yeah, store whatever is in the accumulator into some memory address. And now how do I do that? I think we just need to put that address in it and it will store immediately. There was some other reason, like other way of doing this was there. I don't know. We'll try it. Okay, what did they give us? What's the address? 2500. But still, for just surety, let's check if that is the correct thing. This was not supposed to happen. So data transfer, just want to store sta address. Yes, that's how it should be. And how to store into the memory address that HL pair has. Oh, we could just use this thing instead for that. So that's why they didn't have it. Oh no, you do have it. So you could also use this thing. That's pretty cool. Okay, that is nice. So now we store this into that. Yes, and that's it. Now we don't need to do anything more. So let's try to compile. Your code has been compiled and loaded to memory location. Now we need to execute to see the result. So we'll execute one at a time. So it loads H with 2000 the first step. Let's do it. Yes, that's how it. Oh, this is a stack pointer. This is the HL pair. Yes. Next, it loads B, right? Then it moves whatever. Oh, so A just becomes 0 0. It was already 0 0, but like whatever. Then move on. Add M. So it incremented H. Where is our H now? Okay, it's 2001. If we move on, it adds, and now it's this thing 22. And then loop. So we jump back to the loop, and then it adds to that. Shouldn't it add though? What happened to the add? It didn't do anything. We did increment H and something went wrong. Oh, it was 0. That's why I didn't do anything. Okay, and now this loop, right? It changed. All right, cool. So 2500, we're gonna see what happened to that. 2500. So it became 88 as we thought. So yeah, that's how we can do it. Next question. Write an assembly language program to add two binary coded decimals stored at locations 3500H and 3501. Place the result Okay. That's kind of weird. So two binary coded numbers stored at these locations, right? Place the binary coded result in location 3502 and onward starting with LSB. So that's a problematic thing because now you have to like do it individually with each nibble, and that's not a good thing. So how would we do this? Hmm. Come on, think. Keep on thinking. Uh, Come on, man. How would we add two binary coded numbers? So it's two separate nibbles, and you want to add it like normal decimal numbers, not hexadecimal numbers. How would you do that? Look, each nibble represents a digit, and yes, it can represent all of those as well. So that's a good thing. And then you need to add it such that you can carry. Oh, this is getting bad. So what if you just add it directly without carrying or anything? Then that's gonna be a hexadecimal number, right? So yeah, but the first guy, that's actually whatever is in the first, the higher nibble, that times 10. That's what the first thing is representing, and that's a problem because it doesn't work that way. So oh god, how am I supposed to do this? Can't think of it now. Should you take both of those nibbles separately and then try to add those? Maybe. Like if we do that, yeah. Uh, but then the first guy, it's supposed to be into 10, right? Like the higher nibble. How would we do that? For normal numbers, it was pretty easy to just add. But then for this thing, not so sure. Maybe we can like compare each nibble and with 10 and then set a carry, right? Okay, this is bad. How do we start? How do we start with this? I know how decimal addition works, but then doing this in some other number pattern, like how is this supposed to go? How is it even going to work, right? Come on. Maybe you can like first of all convert these back into 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 hexadecimal number, then add those and then convert it. That would be very bad. That's probably even worse than what we are trying to do. Okay then. So what's our idea? What we'll do is we'll separate the nibbles. I know it's a bad thing to do, but that's what we'll do. We'll separate the nibbles. We'll add those up. Okay, the problem is that 9 plus 9 is 18. So if the last two digits of these numbers were 18, then it would put one out, and yeah, like uh, how do I deal with that then? Oh, come on. We'll just try to do this like, oh come on, this is not gonna work. This is just not going to work. I can just feel it. It's just not going to work. Uh, Fine. Let's move to some other question because this is too complicated. I don't know what kind of format these binary coded numbers are in. Is it tagged format? Is it unpacked? Do they have one nibble like representing one digit, or a whole byte representing a digit, something like that? I have no idea. Okay, let's move to something else. Write an assembly language program to subtract the number stored in memory location 3601H from the number stored in memory location 3600H. Store the positive result. Oh, so you can also have a negative thing. Oh, this is bad. This is okay. We can also have negative numbers with it, but you just want to store the positive result at 3602. Hmm. So 3601, it has some number, 3600 has some number. You wanna subtract the number stored in 3601 from the 3600 number, and whatever result you get, you wanna take the absolute value of that and put that in 3602. Hmm. One thing, what can we do to make this happen? What happens if that number becomes negative of all things? If it becomes negative, then it will you go into the negative numbers, and then your sign will change. It will become like, yeah, the accumulator will put s equal to 1 after that, right? And once the sign changes, how would you get it back to the positive numbers? How would you do that? So then you can just do 00 minus that number, and that would do it. Okay, right, 00 minus that number. Maybe that would work. Or like you can take the complement of this thing, right? I mean, isn't that how they do it actually? No idea. That process is also just complicated. How it actually works, right? So we just do 00 minus that. Maybe that would work. Okay, so let's just erase all of this. Ah, can't I select? Oh, I am selecting. It's just that it's not showing. Right. So load into H. What do you want to load? 3500 and 3501. 3500H. Okay. Then we just want to subtract, yeah, from this number you want to subtract something, right? So we want to actually in fact put this into the accumulator first. So we'll move this to the accumulator, and we are moving from memory. Okay, and then what? And then we'll increment H. So in that case it will now point to 300, sorry, 3501. Yes. And now whatever you have, uh whatever value it has, we'll move it to, or we could just compare it directly because that's not too bad, is it? Right, we could directly subtract from memory. Yes, so we'll increment H, and after that we'll subtract from memory directly. So SUB from memory. Okay, yes. So now you subtracted. Now you happen to have, if you happen to have uh, that negative sign over there. So we want to check this if that's the case. So we'll put an if label. So jump on positive, No, wait. Okay, wait. You can jump on negative. Okay, okay, what? Wait. Jump on negative should be JN, right? Or what is it? JN logic. No, we want jump operations. What was jump on negative? Jump JM. Oh, minus. Right, it's not positive, negative, it's plus or minus. Okay, cool. So JM. So if it's minus, that is okay, it was sign equal to 0 or what? Oh god. If sign is 1, then jump on minus. Yes. Right. To where? We'll figure that out. And yeah, if it's not the case, if that's not the case, then you want to do something like you just want to report this. Okay, wait. Now, you know what? I'm gonna jump on plus. I'm gonna jump on plus to the final thing that would be like the ending statement, which is just reporting whatever is in your accumulator to what value was this 3502, right? So just increment h and you would just say move from accumulator to to the memory, right? So ma, that should work. Yeah, and this statement, this is where I want this to jump. So we'll just call this thing, I don't know, call this thing A. Oh shit, it's not something like that. Okay, so just jump to A. If your if this was positive, right, then directly jump to A. If it was not, then I want to make this different. So I'll just say that what do I say? Move immediate. Make it A 00H. Okay, and then I want to subtract this guy. There's no borrows or anything, I think, right? That's how it is supposed to be, right? Signed integers and everything. So subtract what? Subtract wait. When you subtract m, now this thing is in, oh shit, it's not supposed to happen. Okay, we'll just do this. We'll first just put it in the memory, and if it was negative, it's bad, it's really bad. This thing, we will skip this for later, so just control C and delete. And this too, not talk about that first. So we'll subtract m, increment h, move it to that. That's how the normal flow should be. Now after this we will check if it's 0. So it's still, the accumulator still has, yeah, the sign flag that didn't change, right? So we can still check it. So we'll jump on positive. So if it was positive, no worries, just jump on our halt statement, right? So stop. So we'll jump on stop if nothing bad happens. If it is bad, like you have a negative value, then what I want to do is just the m guy, it still has the location of what, the location where we are storing, right? Yes. So we'll move immediate to A00H, and now we will subtract M once again. So this double subtraction, supposed to be capital M. So this double subtraction will probably make this into a positive number after this, right? And now whatever is in A, we'll just put that back into M. So we'll move to M from A. This should probably work. Okay, so let's try to put some values in there. So we want 3500H. Right, we'll start from here. We'll just put two numbers, and I want the first number to be deliberately smaller than the... Oh, we wanna subtract from 3500 or... Yes, from 3500. So this should be smaller, because then only it will show what I did is correct or not. So we'll have it as, I don't know, 22. That's not a good thing. Oh, that's not a good thing, because this is now an unsigned integer. That's not supposed to happen. Oh shit. How do we deal with signed integers then? Uh-oh. We'll just try to see if this works. Okay, this should... still try it. And this I would just put 33. 33. It's not 33 anymore. And we'll see if this works or not. So compile and run fast forward. This is 11. Oh, this worked for some reason. Compile. We'll start doing this. So first it loads into H3500. So right now this is 3502 from the previous run, and when we do this it's now 3500. Then it moves into accumulator whatever is in the memory, 22. Then it increments H, then subtract. So it's EF93. Oh, huh, EF. Yeah, how is that supposed to make sense? So it's dealing it as a sign. I have no idea how that works, but if it works, it works. Okay, next. I get it that the sign, it has D7 being equal to 1 and stuff, but it's still kind of weird, because why isn't it considering as an unsigned int, and it has to consider it as a sign. And there's only one algorithm that they use in the arithmetic logical unit to actually subtract and add and all of it. So maybe that's how it works, even though it probably shouldn't. And yeah, it just works out. So it didn't stop, and now it's changing. So we move this to 0 0. Right now it's EF over here, and now when we do subtraction, this becomes 11. Cool. Hey, so what I thought was correct, it did work. So that's nice. It's actually nice. Next question. Write an assembly language program to count number of even data bytes occurring in a block. Wait, is that question? Write an assembly language program to count number of even data bytes. Even data bytes. What? Occurring in a block stored from memory location 3001 H and onwards. Yeah, even data bytes. Occurring in the memory block stored from memory location 300 on H. The length of block is stored in 300H. Store the result in location 316. Wait, but how do we know if the number is even or not? Oh. How would we know that? Yeah, like it being even. mm, Hey, what that means is that like if it has to be even, then its last, sorry, it's like it's 2 power 0. That digit must be 0, and then it would be even because everything else is just 2 to some positive power. Oh, so that's not that bad. All we need is just the last digit. So what we can do is just find out what the last digit is, and after that compare it with something, right? So we'll compare it with 0, and if it's equal, then we'll say it's an even number, and like that. Okay, that's not that hard. And we are starting from, so the length of the block is stored in 300H. Okay, and and we start from 3001, and we want to store the result in some location 3100. Okay, so instead of moving this to A, we'll just move this to B. And then of course the increment H. So now we actually start. So we are starting 001. Okay, and then we will move this. So right now I'm just doing this for the first thing, and then we'll try to loop this. So subtract, and no, that's not what I want to do. Instead I want to put this into a calculator. So move move into the calculator from memory. Okay, and next what I want to do, okay, next what I want, what's all of this? Okay, just delete all of this. Cool. So you move to the accumulator now, and now we just want the last digit of this thing. So what we can do is just take its what should I say this? It's AND. Yeah, it's AND operation with something that will make it right. I know how to do it. How do we take an option? An immediate, I think, right? And immediate, of course, with the accumulator. And the data that I want to put is uh, 0, 1, right? H. What this will do is, since all of the other bits other than the 2 power 0 bit, everything else is just 0. So it's AND with whatever is in H, that will just return 0, and the 2 power 0 bit is 1. So if in accumulator you have the unit digit as being, or 2 power 0 digit being 0, this will give 0. If not, then this will give 1, right? So if it's 0, it's even. So now we already have something for the sign, I think. Wait, do these operations actually change the the flags? We just have to see that. This is arithmetic and logic, I think. So so carry is cleared, but nothing about sign flag is given. So yeah, just for surety, I think we should go for comparing first. So carry is cleared, right? That's a problem. So we cannot do it directly like that. But it can like give the result 0, and wouldn't Z be set by this? Or do you actually wanna compare to 0, 0, sorry, to 00H? Is this what you wanna do? No, I mean, doesn't it already imply like the result is 0? So doesn't it imply that it already becomes 0? Yeah. Okay, if that's the case, if it is 0, then we can probably do it directly without comparing or whatever, right? Or you could just compare, but we'll just do it directly. So since this gave us 0, if it was an even, we want to jump. Oh, we also need to set a counter for how many even numbers there are. So we'll just do move immediate, choose some register, say C, and into C we will put 00H. So this is the coin. This is the counter. Right now it has 0 in it. So if right, if this was 0, then what I want to do is do it like that. And otherwise, we don't want to do anything with the C. So we'll just jump on not 0 to odd. Okay, and our odd is basically just do nothing. So NOP. That's not supposed to happen here. Oh, okay. This is now on that. Oh, this is not supposed to happen. Why did this happen? Okay, anyway, and our even tag. I mean, there's not a need to put this tag, but seriously, just put this. So even tag, it's just incrementing C. So INR C like that. Right. So incrementing C. What was I doing once again? Right. And then what? After we are done with it, we are done changing C. We want to decrement what? Decrement B so that, right. So we will just decrement, right. And now we just want to loop this. So we will just jump to the loop. And where do we start loop? Say loop. Where do we start the loop? We'll start the loop from this thing, right? No, wait. But it does this every time. Okay, it's all right. It's all right. We can definitely do it. So this is where we start the loop from. So increment H in the loop. Then we'll move whatever is in M to A. Then we will A and I 0 1 H. That means we'll do AND with 0 1. Then we will. It should be like capital Z over here, but I think it's not case sensitive, so it still works. Alright, so once we are done with it, we will have something in C, and that will be how many of even numbers there were. And what do we do with that information? Store the result in 3100. So store yeah, there was something for this one, or you could just move into some kind of address, but whatever, fine. What was the thing? 35 what? 3100. And then after this we will put this thing, some move into a memory from C, I think. Yes, that's how it should be. Okay, so it starts with 3000. We should just go to 3000. So we'll start from 3000. I'm gonna put some stuff over here. Let's say it's first one is odd, second one is 0, which is an even number, and this is, for example, say 2 is also an even number. And this is probably hey, wait, no, 300, that has the number of numbers basically. Oh, so this should be odd, I think. Okay, and this would just be right. So there's 2 odds, 2 evens, and we'll have 4 in here. Okay, cool. And now we can start. Let's see if this works. So we just run this. Hey, run this fast forward. Infinite loop in our code. But I do have the halt instruction. What's the problem of that? Okay, stop. Where did I have an infinite loop? Huh? Okay, let's just run this from 1 to 1. So it loads. Right, it loads into H 3000, then it does this thing, then it moves into B4. Okay. Oh, oh no. Oh, I understand what went wrong. So I did decrement this, but I didn't actually get out of the loop. That's the problem. What's this? Jump on. Ah, it should be jump on non-zero. And that's why there was an infinite loop, because it didn't matter what B was doing, it just jumps like. What the hell? Okay, now it should probably be running. So we'll just compile and now we'll run. And yeah, there we go. It should be doing something for 3100, which is somewhere over here. No. 3100. Can I just, okay, 31. So it's 2. Yes, exactly. So this is working. That's nice. And let's go to the next question. A hex number is stored at some location 3000. Write an assembly level language program to interchange its digits. Wait, what? Oh, so it's a hex number and just want to interchange its digits. Just 2 digits basically. The new number is to be stored at. So changing the digits, you just change the nibbles. Each nibble having the same order of bits, right? It's still the same thing. It's just that the nibbles are switched. Oh, we know how to do this. We could just rotate 4 times, and that would switch the nibbles basically. So yeah, that would be a nice thing. So okay, it's in 3000. So we already have that. Why even do this? Just load it directly to the accumulator. So LDI, I think, is that? No, LDI is not. Okay, let's look at this once again. For accumulator, it is LDA. LDI is not there for accumulator. It's just MVI, which is for any register in general. But for accumulator, it's LDA, and LXI is for register pair. Okay. So it's LDA. And we load this from a memory address, right? Once again, what was this? It was from a memory address, right? What else could it be? Oh, okay. LDA, loads content of memory address into register A, right? Cool. So we'll do that. We'll do exactly that. It's 3000H. Okay, after that we just wanna rotate this. So rotate to say left or right. It doesn't make a difference, does it? So just say rotate right to carry, whatever that does. And once again rotate right to carry, and rotate right to carry, and rotate right to carry. Okay, and now it would have switched, so we'll just store that whatever A is into this thing. So just say STA, probably that's how you do it, right? That's how you store into some address. Hey, isn't that how it works? We'll try to compile this. Oh, it has been compiled. Cool. But we'll stop, and we need to put something in 3000. We already have put something, right? But let's put something that has, okay, whatever, just do this. So 3001, it should put it over there. So we just fast forward everything. 40, exactly, that's how I wanted it to be. So this is actually very easy, and I just want to check if rotate to right would have also worked the same way. So Control C and boom, Control V, Control V, Control V, Control S. I don't need to save, it's just online, right? So no need to save. Right. And now if I do this, it does 80. Hey, how's that supposed to happen? Why did it do 80? It should just store A. Okay. It's still storing is 80. But why? Why is it storing 80? So the thing is, I think RAR is working differently than what. Yeah, that must be the thing. So yeah, this doesn't work. Just use RRC and that will work, I think. Okay, next. Next we have write an assembly language program to count the number of times the data AD in hexadecimal is found in a block of memory locations starting from 300H. Length of the block. Hey, it's the same thing as that thing where you had to search for even numbers. Okay, fine. So what's this like? It's just load into H pair address, length of the block stored in location 2FFFH. What? Oh, that is weird. Okay, but in H we'll just store 3000. Then we'll load to. We can't move from addresses directly, that's the problem. I just wish we could directly do this for any register, right? Ah, maybe we could do like load immediate and some just load immediate is not a proper command. You will first of all have to load it into accumulator. So we'll put put this address which is 2ff f h. Okay, then we will move this. So we'll move whatever is in the accumulator that will be moved to that will be moved to say B, for example. So move to register B. Okay, then what? So we have the count, we have the first term of the series, the location of the first term, and we'll say load. Oh wait, it's move immediate. I think so. MVI accumulator. What do you wanna prove? AD. Okay, and then we'll just compare all of the time. So a loop will start here. So we'll increment h. Okay, no need because it's already the first term. So no need to increment h at first. We'll do it at the last. Using this h, we'll just compare with a. Sorry, we'll compare with because it's already a in there. We'll compare what memory location. That's M, I think. Okay, so when this is 0, then okay, when this is not 0, then I want you to jump to, let's say, something called some label called f. No, well, f is yeah, f is not a label, so it works, I think. And here I'll just put f being this label. Where is it? Where is it? Where is that? Ah, yeah. The label will be what? What's the command that whatever? Just put NOP because I'm not able to think what we're supposed to do right now. And we are just really trying to like skip whatever is going to be in this line. So if it's not 0, just skip this. If it is 0, then do this. We'll have to increment something. Oh no, but what do we increment? We just want the number of times it appears in this. So we'll make another things like move immediate in C 00H. Okay, now we'll increment C, right? So if it doesn't jump, that is if it was 0, then we'll increment C, and then if it does, right, so it will be here, and otherwise too it will just be here. And what after this? Actually no, just stop putting not, put a proper command. Now since it's 0, you have incremented C, it's done. We just want to get rid of this loop, I mean go back to the starting of the loop basically. So we'll have to decrement B, right? That's our counter variable because that has the number of times that has to be done. Yes, and we'll also increment, oh, first of all, before doing that we should also increment HL pair like that, and then we will decrement B. And if it's not 0, so jump on not 0 to loop. Cool. That's how it should be. So I hope this works. Okay, it 3000. Okay, that's already there. It's 4, and yeah, it doesn't have ADH in there. I'm gonna put ADH somewhere. AD. There we go. Okay, let's run this. Oh, we didn't store it. Why didn't we store it? Uh, yeah. So once this is done, you have how many times did it run in C, and we're gonna store whatever is in C into where is it? Location 200. So we're gonna store this into location 2000. So yeah, how do we do that? Just STA. I think that's how we do it. So store the location 2000H, and that should be working. Right, that should be working. Okay, let's try to run, and we'll just run the program. And now hopefully in 200, okay, in 2000 we'll have something. We have AD as, wait, what? No. Why? How did this, what is in 300? Okay, all of this is just 4 of these. Yeah, well, okay. Shouldn't 2000 have, why is this not, how does this not go? Jump on non-zero to the loop, and when it does become 0 and you decrement b so much that it becomes 0, should this be 300? Like, I don't get it. Shouldn't it have 1 over here? Why is this having AD of all things? Oh, because it's stored accumulator. That's not okay. Whatever. For a normal register, don't do this thing. Loading edge, immediately what? 200. And then move to memory from the accumulator C. Sorry, from the register C. This should probably work. And now if I run this, look, it's 1 over here, exactly how I wanted. Okay, this is it. Now that's like 3 programs. That's enough. That's enough practice. It's gonna memorize all of the other things, and yeah, this should be enough. Yeah. So I'll see you guys in the next video. Bye.